then we go up and up with our end behavior. So the limit of our function as x goes to negative infinity would be positive infinity, right? It's going up. And the limit on the right end as x goes to positive infinity would also be positive infinity. Therefore, these limits do not exist. We could write d at e. We could use this notation as well, but those limits don't exist. Therefore, there are no horizontal asymptotes with this function. Likewise, in the second example here, here is a polynomial's end behavior if it's got an odd degree, if the leading coefficient is positive, but we have a negative leading coefficient. So our end behavior will look like this, right, with a negative leading coefficient. So our limits on both ends, I'm going to go to the left side first. This looks like q of x. And I should have really used p of x up here, but so be it. Okay, so with q of x, if we go to the left, it looks like our limit would be positive infinity, and our end behavior on the right for q of x would be negative infinity. Therefore, neither of these exist either. Technically, they do go to negative infinity, but there's no horizontal asymptotes. So the limit is determined by the behavior of the leading term. Why? Because that leading term is overpowers the others, right? Overpowers, or you could think of it as takes over as x goes to either positive or negative infinity. So let's look at an example of rational functions. 3 different scenarios you could end up with polynomials written as rational functions. So our degree here and here you could see is the same. Now if that's true, as x goes to infinity, these terms here are not going to have the strength that these will as x gets very large. So they kind of become meaningless. So really we're taking the limit as x goes to infinity of 3x squared over x squared. And when we reduce that, these two terms have an equal amount of strength as x increases. What we get is this, and the limit of any constant would just be that constant. So x, there is no variable remaining, so therefore we would know that there is a horizontal asymptote at y equals 3. Okay, another example. Now in this example, what you'll see is that we have a power, the degree on the top and the degree on the bottom are different. And since the degree on the top is lower than the degree on the bottom, of course these terms will not make any difference in the long run as x gets extremely large. What we get is this x to the 4th over x to the 5th. X to the 5th will overpower x to the 4th. Yeah, you could write it in a simpler form like such. 1 over x, right, if we did that. And then just did direct substitution. As x goes to infinity, this thing will go to 0. So if the degree on the top is ever smaller than the degree on the bottom, their coefficients won't matter at all. What we'll get is a horizontal asymptote at y equals 0. Hence why when we looked at that example earlier of 1 over x, it went to 0. Now in this third example, we've got an example where the degree on top is larger than the degree on the bottom. And so when we just negate these unnecessary terms on the end, we get the following expression. We get negative x cubed over 2x. And when we simplify that, that x cubed is going to overpower that 2x in the denominator, and we'll get this right here. As we do a direct substitution, we're going to get negative infinity squared over 2. And that, as x continues to get larger and larger, will just continue to go to a larger value of negative infinity. Therefore, that would not exist. Oops, didn't want to do that. Wanted to do that. If the degree on the top and the degree on the bottom are the same, we're going to divide their coefficients. If the degree on the top, like in example 2, is smaller than the degree on the bottom, our horizontal asymptote will exist at 0. And if the degree on the top, as we see here, is larger than the degree on the bottom, there won't be any horizontal asymptotes and the limit will not exist. Okay, let's look at the analytical side of things. And what we're going to do is we're going to divide, at least in the first example, all terms by x to the n, where n is the largest power in the denominator. Okay, and this one is a little bit tricky. So I'm going to do it a couple different ways real quick. I'm going to do the analytical method, and then I'm going to do just more of an intuitive method. So what is the largest degree on the bottom? Well, that can kind of be interesting. Okay, the degree is not 2. The degree is actually just 1. Why? Because the square root, right? The square root of x squared is actually x. So what I'm going to go ahead and do is divide everything in the bottom by x. And that means I'm going to divide this by x as well. Okay, this is the analytical way of doing this. Meaning I'm going to manipulate this algebraically. So in the numerator I get x, right? Because x squared over x is that. Over here I get 1. In here, if I were to bring this x inside, I have to make it x squared. So I get x squared over x squared plus 1 over x squared. Okay, so let's see what we get. It looks to me like we get the limit as x goes to infinity of x over 1 plus, and in the square root I get 1 plus 1 over x squared. Okay, so I should probably write the limit notation here to be official about it. So if I take the limit as x goes to infinity of this thing, right, what will I get? Well, I'll get infinity over 1 plus the square root of 1 plus 0, it looks like to me. Right, as x goes to infinity, this term is going to go to 0. So what do I get? Let's analyze this a little bit more. I get infinity over 1 plus 1, which is 2. Of course, when I divide infinity by 2, that's not going to make any difference. Therefore, this limit would equal infinity and therefore does not exist. Okay, another way to do this problem would be the following. Okay, as x goes to infinity of the original problem, I'm going to look at this, instead of in the analytical method, I'm just going to look at it with a little bit of intuition and some logic. Okay, so as x goes to infinity, this 1 is not going to matter at all. Okay, I'm going to rewrite here in a moment. And I'm going to leave x squared here. I've got x plus the square root of x squared. Well, the square root of x squared is really just x. And therefore I have x squared over 2x. So if I were to do some reducing, this would just really be the limit as x goes to infinity of, it looks like, x over 2. And as x goes to infinity, I get infinity over 2, which, as we saw earlier, does not exist. Okay, so what that's telling us is that there is no horizontal asymptote. This function is going off to infinity. All right, let's look at example 5, e to the negative x. If you look at the graph of e to the negative x, it's going to look something like this. Okay, where this is the point 0, 1. Okay, and as x goes to infinity, you probably can tell just from the graph that this is going to approach 0. Terrible color choice. Another way that I could do this problem analytically, a little bit more than just looking at it graphically and having common sense, is this. I could change the exponent on e to the x to be 1 over e to the x, turning that into a positive. And then direct substitution, well, that's going to become a very large number, which means that would be 0. So we can check that off in a more analytical sense or just looking at it graphically. So what does that mean? That means that there's a horizontal asymptote at y equals 0. All right, natural log of x. I'm just going to look at this one graphically, but there's a graph of the natural log of x. It has a vertical asymptote at 0. And some are tempted to think that there is a horizontal asymptote that exists, but there isn't. Therefore, the limit as x goes to infinity of natural log of x is infinity, so it does not exist. There is no horizontal asymptote. Okay, last example. It's kind of funky, but I like it. I'm going to use properties of limits to rewrite this. So here is the limit as x goes to infinity of 5x over x. I'm splitting this up. Plus the limit as x goes to infinity of sine of x over x. Now this piece right here looks really close to something that we've looked at as a limit to memorize, but it is not the same. Our limit there, we said as x goes to 0, that would go to 1, but this is as x goes to infinity, so don't be fooled with that. Okay, in the first limit, we see the x's will cancel, and therefore the limit as x goes to infinity of 5, right? So of 5. This is just the value 5, y equals 5. X is not going to change that at all if y is always 5. Therefore, this will be 5. Now over here, this is a little bit different, but I want you to imagine the graph of sine x, right? And it goes on forever. Well, it would hit a maximum value of 1 and a minimum value of -1. Therefore, worst case scenario, this as x goes to infinity, the maximum value that could be is 1. The minimum value could be is -1. But x is increasing without bound. Therefore, we get this oscillation in the numerator, but the denominator keeps getting larger, so that would be 0. And therefore, our limit would equal 5. So we have a horizontal asymptote there at 5. All right, let's move on to the next slide. Okay, I got some work to do and not a whole lot of time to do it. So what I'm going to do is just kind of work through this quickly and take questions in class if you have it. So I'm going to take the limit and I'm going to do a poor job of foiling, and there's a reason. Okay? I don't care about foiling the whole thing out. All I care about is the leading terms. See how these will cancel? That tells me that my horizontal asymptote will be at -2. Okay, so it looks like b would equal -2. Okay, for the next one, I'm going to do a similar method. I'm going to go ahead and do a poor man's FOIL. And on the bottom, I'll get this -a squared x squared. I don't care about the rest. I just care about the leading term. And therefore, I see the limit as x goes to infinity of 2x squared over a squared x squared. I want to equal 2/9. Okay, so you see that the x squareds, they drop off. So I get 2 over a squared equals 2 over 9. It looks like to me a has to equal 3. Okay, last couple of examples. We're just looking in number 10 for which function will overpower the other. And in this case, x to the 100th will be much stronger than natural log of x. Therefore, the denominator will overwhelm the numerator. So our limit will go to 0. So this would be a yes. In the second one, e to the power of x is way stronger than natural log of x. So there would be no horizontal asymptote. Okay, the limit of that would be infinity. And here, this is a tough one, but e to the power of x will eventually overpower x to the 100. So we would get y equals 0, and therefore this would be yes. All right, last question here. Find the horizontal asymptotes. Looks like there's 2 of them. I'm going to do a left end behavior and a right end behavior, and I'm going to come back and explain it so I don't run out of time here. Okay, so the left end behavior you'll see over here, as I plug a negative infinity in here and here, both of those terms are essentially going to become 0. All right, so I get a limit as we go to the left of 5, right? That's 5 over 1. So I get a horizontal asymptote of y equals 5 to the left end behavior side. On the right side, this 5 and 1 become irrelevant because when I raise these to the same power as x gets infinitely large, they're going to act the same and they're going to overpower the 5 and the 1. Therefore, it looks like on this side, I get -1 as my horizontal asymptote.